All right, this is question number 4 from the 1999 AP Calculus AB exam. It's a function FRQ. We're given a function with a continuous second derivative for all x, and we're told that f of 0 is 2, f prime of 0 is -3, and f double prime of 0 is 0. And also g has a function that is a derivative of this. I'm not going to read all that out, but that's the derivative of g. We want an equation of the line tangent to f when x is 0. Well, that should be pretty straightforward. If f of 0 is 2, we have the point 0, 2, and f prime of 0 is -3. We just write y equals our slope of -3x plus our y-intercept of 2. And that's all there is to part A. 1 point for part A. In part B, it says, is there sufficient information to determine whether f has a point of inflection at x equals 0? Now, we can see that the second derivative of f is 0 at x equals 0, which means it could have a point of inflection, but we don't know if the sign of the second derivative is changing there or if it's staying positive or staying negative. So we're going to say no. We do not know if f double prime of x changes signs at x equals 0. And that's worth 2 points. 1 for no and 1 for the reasoning. In part C, it says, given that g of 0 is 4, write an equation of the tangent line to g at 0. Well, we're going to use the point 0, 4, and we just need to find g prime of 0. Well, we're given g prime. It's e to the -2x, so that'll be e to the 0, times 3f of 0 plus 2f prime of 0. E to the 0 is just 1, and f of 0 is given to us as 2, so 3 times 2 is 6. And f prime was given as -3, so we have 2 times -3, so that's -6. And so we just end up with a slope of 0. So if our slope is 0, it means we have a horizontal line, which means the y value is always just 4. So the equation of our tangent line is y equals 4. And they gave you 2 points for that. 1 for getting the value for g prime of 0, and 1 for the equation. And in part D, it says, show that g double prime of x is equal to that big expression that they gave us. And then it asks us if g has a local max at x equals 0. And so first we have to show that g double prime of x is equal to that. So g double prime we'll have to find using the product rule, because it's a product of e to the -2x and 3f of x plus 2f prime of x. So that'll be the first function, e to the -2x, times the derivative of the second function. So that'll be 3f prime of x plus 2f double prime of x. And then we'll add to this the derivative of e to the -2x, which is -2e to the -2x using the chain rule, times 3f of x plus 2f prime of x. And now they've clearly factored out the e to the -2x, so we'll do the same, e to the -2x. And now when I take that out, I've got 3f prime of x plus 2f double prime of x. And then I'm left with a -2 times all of this, so minus 6f of x, and then minus 4f prime of x, which gives us e to the -2x. And then we've got a -6f of x. We've got 3f prime and -4f prime, which will be -f prime, and then 2f double prime. So that's our verification. That's exactly what they wanted us to show that g double prime was. It's the same as what they got up here. And then it says, does g have a local maximum at x equals 0? Well, we know just from a second ago that at in part C, g prime of 0 does equal 0, so it possibly does. So we'll say g prime of 0 equals 0. And then we'll find g double prime of 0. Well, g double prime of 0, e to the 0 is just 1. And then it's -6 times f of 0. So -6 times f of 0, which was 2. And then minus f prime of 0, so minus -3 or plus 3. And then plus 2 times f double prime of 0, which is just 0. So g double prime of 0 is -12 plus 3, which is -9, which is less than 0. When the second derivative is negative, we know the function is concave down, which means there is a maximum. So we will say, so yes, there is a max at x equals 0. And they gave you 4 points for this. 2 for the correct verification of the derivative. 1 for g prime of 0 and g double prime of 0. And 1 for yes with the reasoning that we gave. And that's the end of this function FRQ. Is question number 4 from the 1999 AP Calculus AB exam. All right, this is question number 6 from the 1999 AP Calculus AB exam. It's a function FRQ where we're given a function 1 over x squared and its tangent line at a point P, right, where we're saying we have the coordinates of w and 1 over w squared. And then we have point Q, which is just directly below it on the x-axis, w comma 0, and its tangent line at point Q, or sorry, at point P, the tangent line at point P, which crosses through the x-axis at point R, k comma 0. We want to find the value of k when w is 3, which means we need to find the equation of the tangent line of that line L, right? So we know that the point is just the point at x equals 3, right? So it's the point 3 comma 1 over 9. And then we need the derivative. We need to find dy dx when x is 3. Well, the derivative is just negative. The function is x to the -2, so its derivative is -2x to the -3, or -2 over x cubed, which when we evaluate that at 3 gives us -2/27. So the equation of the tangent line there is just y minus our y value of 1/9 equals our slope of x minus our 3 value, right? And so we want to find what k is when this crosses through the x-axis. So that'd be at the point k comma 0. So we'll put in 0 for y. So we get -1/9. And we'll put in k for x, -2/27 of k minus 3. And now we're just solving for k. So we have -1/9 equals -2/27 k. And then plus, because it's -2/27 times -3, so it's going to be a plus 6/27, which is just 2/9. Subtract the 2/9, we get -1/9 minus 2/9 is -3/9, or -1/3 equals -2/27 k. And then cross or multiply by the 27, divide by the -2, and we get k is equal to 9/2. In part B, we should, they gave you, how many points do we get here? We got 2 points for that, 1 for the correct derivative value here, and 1 for the answer. And then in part B, it says for all w greater than 0, find k in terms of w. Well, our slope, as we just found a second ago, right, our slope at x equals w is just going to be -2 over w cubed. And our point is now just going to be the point w, 1 over w squared. So our tangent line equation here is going to be y minus 1 over w squared is equal to -2 over w cubed times x minus w. And we want to find k again. So we're going to plug in k for our x and 0 for our y. So we'll have negative 1 over w squared equals negative 2 over w cubed times k minus w. And we'll just solve for k. So we have negative 1 over w squared equals negative 2k over w cubed minus a negative, it's actually going to be plus because it's negative 2 over w cubed times negative w. So that'll be 2 over w squared, right? Because we are canceling out those w's. We'll subtract the 2 over w squared to get negative 3 over w squared is equal to negative 2k over w cubed. We'll multiply by the w cubed, right, which is just going to give us negative 3w equals negative 2k, or k is equal to 3 over 2 times w. And they gave you 2 points for that. 1 for this equation down here relating w and k, and 1 for the value. In part C, it says, suppose w is increasing at a constant rate of 7 units per second. And they want to know when w is 5, what's the rate of change of k with respect to time? Well, we just said that k was equal to 3/2 w, which means that dk dt is just equal to 3/2 of dw dt. And we know what dw dt is. It's 7, right? It's increasing at 7 units per second, so it's a positive 7. So dk dt should be 3/2 times 7, which is just 21/2. And they gave you 1 point for that answer. And then our last part here, part D, says suppose w is increasing at that same rate of 7 units per second. When w is 5, we want to know what's the rate of change of the area of that triangle PQR with respect to time, and to determine whether that area is increasing or decreasing. So the area of that triangle, it's just a triangle, right? So it's 1/2 the base times the height. Well, the height's really easy, right? The height is just 1 over w squared, right? Because we're talking about at the point when we're talking about at point, when we're at point Q or point P, right? Our x value is w, and then our base is just the distance between R and Q, right? And so the distance between R and Q, right? This is the point K, 0, and this is the point W, 0. So the distance between those is just K minus W. And so our area formula ends up being 1/2 of K minus W times 1 over W squared. And we are looking to figure out the rate of change of that area. And it would be helpful if we could get this all into terms of W, right? Which we do know how to do, right? Because if we look back here, we know that K is equal to 3/2 of W from part B, right? So I can now call this 1/2 of 3/2 W minus W times 1 over W squared. Well, 3/2 of W minus W is just 1/2 W. So I've got 1/2, and then I've got 1/2 of W, and then I've got 1 over W squared. And so it looks like we're going to end up with 1 over 4W as our area. And so now we want to find the rate of change of that area. So we need to take the derivative with respect to t, right? And so this is also kind of like 1/4 of W to the negative 1, if that's helpful. So dA dt should just be negative 1/4 of W to the negative 2 times dW dt. And so now if we're going to evaluate this when w is 5 and dw dt is 7, we're going to get our dA dt that we care about is -1 over 4 times our w squared, so that's going to be 25. And then we had dw dt, which was 7. And so we end up with -7 over 100. And we'll note that since dA dt less than 0, the area is decreasing. And that ought to get us all of the points here for this. They gave you 4 points here. 1 for the area formula, whether you simplified it or not. 1 for taking the derivative of dA dt implicitly, correctly. 1 for getting this value of -7 over 100. And 1 for saying that's negative, so the area is decreasing. And that is the end of this function FRQ, question number 6 from the 1999 AP Calculus AB exam. All right, this is question number 5 from the 2000 AP Calculus AB exam. It's a function FRQ where we're given the curve xy squared minus x cubed y is equal to 6. And we're first asked to show that the derivative is that expression that they've given us. So we'll take the derivative implicitly with respect to x, and we'll require the product rule for xy squared and for x cubed y. So the xy squared will become x times the derivative of y squared with respect to y times the derivative of y with respect to x. And then plus the derivative of x, which is just 1, times y squared. And then we'll have minus x cubed times the derivative of y with respect to x. And then minus a 3x squared for the derivative of the x cubed part times y. All equal to 0. Don't forget to take the derivative of what's on the right-hand side. We'll now just keep our dy dx terms on the left and factor out the dy dx, giving us dy dx times 2xy minus x cubed is equal to a positive 3x squared y when we bring that over, and a minus y squared when we bring that over. And now we'll just divide by the 2xy minus x cubed to show that we get exactly what they said we were supposed to get, 3x squared y minus y squared over 2xy minus x cubed. And that was worth 2 points, 1 for the correct implicit differentiation and 1 for the algebra to get to the verification of what they said the derivative was. It's for part B, it says find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line for each of them at those points. So if x is equal to 1, we're going to get y squared if we plug in 1 here, minus y if we plug in 1 there, equals 6. Or y squared minus y minus 6 is equal to 0, which we can factor into y minus 3 and y plus 2 equals 0, giving us y values of 3 and -2. So the 2 points we're going to be talking about here are the point 1, 3 and the point 1, -2. So we're going to need to evaluate the derivative at each of those points. So at 1, 3, right, our derivative was 3x squared y minus y squared. So that'll be 3 times 1 squared times 3x squared y, minus y squared, all over 2 times x times y minus our x cubed. And so it looks like in the numerator there, we've got 3 times 3 is 9, minus 3 squared is 9. So we're going to have 0 there. And then divided by something that is not 0. So that's just equal to 0. And so then we'll do dy dx at our other value, which was 1, -2. So that's going to be, again, 3 times x squared times y minus our y squared, so negative 2 squared, over, we had 2xy, so 2 times 1 times negative 2, and then minus x cubed. And so if we evaluate this all out, the numerator is negative 6 minus 4, so that's negative 10. And our denominator is, looks like negative 4 minus 1, so that's negative 5, so a slope of 2. And so we've got two tangent lines, so we'll say at the 1, 3, the first one we did, the slope was 0, right? So that's just a horizontal line, so that's just going to be y equals 3. And at the point 1, negative 2, we'll do y plus 2, y minus negative 2, equals our slope of 2 times x minus 1. And those are our two tangent lines. We got 4 total points here. 1 for getting y squared minus y equals 6. 1 for correctly solving for y. And 2 for the two tangent lines. 1 for each of the tangent lines. And here in part C, it says find the x-coordinate of each point on the curve where the tangent line is vertical. So the tangent line will be vertical if dy dx is undefined, which means that the denominator of our dy dx, which was 2xy minus x cubed, is equal to 0. Or in other words, we can see that if we factor out the x from that, we get 2y minus x squared is equal to 0. So that will be when x is 0, or when 2y minus x squared is equal to 0, which would be when y is 1/2 x squared. So now we need to plug in each of these to figure out if there's actually points on the graph where that's true. So if we plug in 0 here, we can see that we'll get 0 minus 0 equals 6. Well, that's not true. So we're going to eliminate x equals 0. That is not a point on the curve. There's no point on the curve when x is 0. But when y is 1/2 x squared, we'll plug that in. We'll get x times 1/2 x squared squared minus x cubed times 1/2 x squared equals 6. And so we'll distribute all this stuff out, or multiply all this stuff out. This ends up being 1/2 x to the 5th. And then this is minus a 1/2 x to the, I'm sorry, this is first one is not 1/2 x to the 5th. We forgot to square the 1/2 part. It's 1/4 x to the 5th. And this other one is 1/2 x to the 5th. And so now we have negative 1/4 x to the 5th is equal to 6, or x is going to be equal to the 5th root of negative 24. And that is our only x coordinate where we have a vertical tangent line. You got 3 points for that. 1 just for setting this equal to 0. 1 for substituting into the original equation, and 1 for getting the answer. And that's the end of this function FRQ, which was question number 5 from the 2000 AP Calculus AB exam. All right, this is question number 4 from the 2001 AP Calculus AB exam. It's a function FRQ, and we are given a function h that's defined for all x not equal to 0. And h of 4 is negative 3, and we're given the derivative x squared minus 2 over x for all x not equal to 0. And first we want to find all values of x when h has a horizontal tangent, and then determine if it's a max, min, or neither there. So h will have a horizontal tangent when h prime of x equals 0. So that'll be if x squared minus 2 is equal to 0, right? Or x is positive or negative root 2. And we know that clearly that the denominator of that is just x, right? So if I evaluate h prime, like we'll make a little sign chart here, right? With negative root 2, 0, which is another critical value, a place when the derivative is undefined. Right? And so we should probably indicate that, right? H prime is undefined also when x is equal to 0. So we should definitely indicate that. Right, our 3 critical values. Make a sign chart, right? And say, well, if I plug in something between 0 and root 2, like 1, we end up with 1 squared minus 2, which is negative, over a positive 1. So we get a negative here. And if I put in something like negative 1, we get a negative over a negative, which is positive. And if I put in something more than root 2, like a million, we get a positive over a positive. And something like negative million, we get a positive over a negative. So we can see that we have 3 sign changes, which means we have 3 maxima and minima. This one, so we'll just go ahead and say that we have a local min of negative root 2 at x equal, oh, sorry, a local min, not of, negative root 2, a local min at negative root 2. And that's because, I said, and at root 2, local min at root 2, we'll put that one down too. And root 2, because f prime changes, or not f prime, this is h prime. Off to a good start here. H prime changes from negative to positive. And we're only talking about when we have a horizontal tangent. And so at 0, we do have a maximum there, right? This is a max, but it's not a horizontal tangent line there. And so they don't ask us to classify that. If we were asked to, we'd have max there. But as such, we only are asked to classify the ones where it has a horizontal tangent, not where its derivative is undefined. And so we got 4 points there, 1 for getting plus or minus root 2, 1 for the analysis, and 2 for the conclusion here. So 4 points in part A. In part B, we want to know when is h concave up. Well, h is concave up if its second derivative is greater than 0. So we'll find h double prime first using the quotient rule. Denominator of h prime times derivative of numerator minus numerator times derivative of denominator all over the denominator squared, which becomes 2x squared minus x squared plus 2 over x squared, or just x squared plus 2 over x squared. And we'll note that this is greater than 0 for x not equal to 0. And we can say then it is concave up on negative infinity to 0 and 0 to infinity. Or you could just write it's concave up for all x not equal to 0. And they gave you 3 points there. 1 for just getting the second derivative, 1 for noting it's always positive except at x equal to 0, and 1 for your interval. In part C, it asks us to write an equation for the line tangent to h at x equals 4. Well, we're given the point h of 4 is negative 3. So we just need h prime of 4, which will be 4 squared, or 16, minus 2 over 4. So 14 over 4 is just 7/2. So it'll be y minus negative 3 in point slope form, right? Y minus the y value equals the slope times x minus the x value. And they gave you 1 point there for the tangent line equation. And in part D, it says, does that tangent line lie above or below the graph? Well, we already said that h is concave up, right? Well, we said h is concave up for all of these values, right? Everything but 0. But in this instance, certainly for x greater than 4. And when we have a function that's concave up, the tangent line is going to be below that function. So the tangent line is below the graph. And they gave you 1 point for that explanation. And that's the end of this function FRQ. It was question number 4 from the 2001 AP Calculus AB exam. Oh, right. This is question number 5 from the 2001 AP Calculus AB exam. It's a function FRQ where we're given a cubic function, a polynomial, 4x cubed plus ax squared plus bx plus k with constants a, b, and k. And we know it has a minimum at x equals -1 and a point of inflection at -2. And it asks us to find the values of a and b. So in order to have a minimum at -1, that means that the derivative must equal 0 or be undefined, but it won't be undefined since it's a polynomial at -1. So we'll find f prime of x first, which will be 12x squared plus 2ax plus b. And we know that f prime of -1 needs to equal 0. So we'll say that if I plug in -1 here, we should get 0. So 0 is equal to 12 times -1 squared plus 2a times -1 plus b. Or in other words, we end up with 12 minus 2a plus b. So 12 minus 2a plus b needs to equal 0. And then we'll also deal with the second derivative, right? The second derivative tells us when we have points of inflection. So our second derivative is going to be 24x plus 2a. And we know that that needs to equal 0 when x is -2. So 0 when x is -2. Well, it looks like that tells us that a must be equal to 24. And if a is 24, then 12 minus 2 times 24 plus b needs to equal 0. Well, 12 minus 48 is -36. So b must equal 36. And they gave you 5 points there for part A. 1 for f prime, 1 for f double prime, 1 for substituting in -1 and 0 here, 1 for substituting in -2 and 0 here, and 1 for the values of a and b. And in part B, it says if the integral from 0 to 1 of f of x dx equals 32, what's the value of k? So let's go back in and replace our a and b values here. So we now know f of x is 4x cubed plus ax squared, where a was 24, plus bx, where b was 36, plus our k. So the integral from 0 to 1 of 4x cubed plus 24x squared plus 36x plus k dx needs to equal 32. Well, the integral there is x to the 4th plus 8x cubed plus 18x squared plus kx. And we're going to evaluate that from 0 to 1, and it should equal 32. Well, now, when I plug in 0 to all of those terms, we're just going to get 0. So really, we just need to plug in 1, which is going to give us 1 plus 8 plus 18 plus k equals 32. And 1 and 8 is 9, 9 and 18 is 27. And then subtract that 27 over to the other side, you get k is equal to 5. And they gave you 4 points here for that one. 2 points for the correct anti-differentiation. 1 point for having the expression in terms of k. So I guess maybe this one down here. And a final point for getting k is equal to 5. And that's the end of that function FRQ. It was question number 5 from the 2001 AP Calculus AB exam. All right, this is question number 6 from the 2002 AP Calculus AB exam. It's a function FRQ where we're given a function f that's differentiable for all real numbers. And then we have values of f and f prime on the interval negative 1.5 to 1.5 in this chart. And we also know that the second derivative is always positive. In other words, f is always concave up. And for part A, it just wants us to evaluate an integral of 3f prime plus 4. Well, the integral of 3f prime is just 3f of x. And the integral of 4 is 4x. So we're going to evaluate this from 0 to 1.5. So that'll be 3 times f of 1.5 plus 4 times 1.5, which is 6. And then minus 3 of f of 0 plus 4 times 0, which is just 0. So then we'll just use our chart. F of 1.5 is negative 1. So 3 times negative 1 is negative 3, and then plus 6. And then minus 3 times f of 0. F of 0 is negative 7, so we have 3 times negative 7 there. Right, so negative 21. So we have negative 3 plus 6, which is 3, and then plus 21, which is 24. They gave you 2 points there, 1 for the antiderivative and 1 for the answer. In part B, they ask you to write the equation of the line tangent to f, where x is 1, and then use it to approximate f of 1.2 and do some more stuff. We'll just worry about the tangent line to start with. Right, so we know that the value of the function at 1, right, f of 1 is negative 4 from the chart. And we know that f prime of 1 is 5. So our tangent line should just be y minus negative 4, or y plus 4, equals 5 times x minus 1. So there's our tangent line. And then the second part is use it to approximate f of 1.2. So we'll do that next. So f of 1.2 will do y plus 4 equals 5 times 1.2 minus 1. 1.2 minus 1 is 0.2, and 0.2 times 5 is just 1. So we get y plus 4 equals 1, or y is negative 3. And then lastly, it says, is that approximation greater than or less than the actual value? Well, we know that our function is always concave up. And when functions are concave up, tangent lines lie below the function. So the true value of the function is more than the tangent line. So our tangent line is an underestimate. It's less than the true value. So we'll say because f double prime of x is greater than 0, f is concave up, and our approximation is an underestimate, or we'll say is less than f of 1.2. And that was worth 3 total points, 1 for the tangent line, 1 for the approximation, and 1 for it's less than the true value with a reason. In part C, it says find a positive real number r with the property that there is a value c on 0 to 0.5 such that f double prime of c is equal to r. And so this sounds like it's a mean value thing, right? Because we're looking for the second derivative of something equals r. And so we have to look at values of the first derivative. So we'll note that, since f is, f prime, f of 0.5 minus f prime of 0 divided by 0.5 minus 0, right, that should equal its derivative, right, f double prime of c, right, which is r. And so we just need to figure out what f prime of 0.5 minus f prime of 0 is. So f prime of 0.5 is 3, f prime of 0 is 0, and then 3 divided by a half is 6. So r must just be 6. And then we should note that, that if f double prime is always greater than 0 on this interval, right, that tells us that f prime is differentiable, and therefore the mean value theorem should apply, which is what we just used here. And we know f prime is differentiable because we see that its derivative exists on negative 1.5 to 1.5, and therefore it must exist on 0 to 0.5. And they gave you 2 points for this. 1 for just mentioning the differentiability and the mean value theorem, and 1 for finding the value. In part D, we are given a function g that is this piecewise function, 2x squared minus x minus 7 for x less than 0, and 2x squared plus x minus 7 for x greater than or equal to 0. And it says the graph of g passes through each of these points x f of x given in the table above. Is it possible that f and g are the same function? And so we should, if we know it goes through all these points, right, then we need to just check and see about what's going on here, probably with the concavity, because we know that our second derivative is always positive, but if our second derivative of g here is not always positive, then we can be certain that it's not always going to go through. So if I take the second derivative here, g double prime of x, for both of these, it's just going to be, the first derivative is going to be 4x minus 1 for x less than 0, and 4x plus 1 for x greater than or equal to 0, right? But g double prime of x will always equal 4. So it is always still going to be concave up, but we might make the quick note that just a second ago, in part C, we said that the second derivative had to equal 6 on 0 to 0.5. And since, we'll say, and since g double prime of x, f double prime of x equals 6 on 0 to 0.5, right? We can't have a different concavity, of different value for the concavity, right? 6 or 4, a different value for the second derivative somewhere on this interval. So no, f and g are not the same function. Now, another option here would be to note that our derivatives here, so this was one option, right? We got 2 points if we did this, so no with our reasoning, right? But another thing to note would be that here, g prime of 0 doesn't exist, right? G prime of 0 doesn't exist because if I plug in 0 to each of these, for the top one, I get -1, and for the bottom one, I get +1. So the slope as we approach 0 isn't the same on both of these, right? That slope is undefined, but here f prime of 0 is 0, and therefore, again, because f prime of 0 and g prime of 0 are different, again, we can't have these being the same function. And so you would have got 2 points if you did it that way as well. And that's the end of this function FRQ. Is question number 6 from the 2002 AP Calculus AB exam. All right, this is question number 6 from the 2003 AP Calculus AB exam. We're given a function, f of x equals root x plus 1 for 0 to 3, and 5 minus x from 3 to 5, right? And this is a function FRQ. And we want to find if f is continuous at x equals 3. So to find out if a function is continuous, you need to see if the limit exists at that value, if the function exists at that value, and if they are equal. So first, does f of 3 exist? Yes, f of 3 exists. It's root 3 plus 1, which is 2. Does the limit as x approaches 3 exist? Well, we have to do the limit from the left and the limit from the right and see if they equal each other. So the limit from the left is just the same thing we just did. It's root 3 plus 1, which is 2. And the limit on the right is 5 minus 3, just the 5 minus x part, which is also 2. And since the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right, the limit as x approaches 3 of the function as a whole is the same value. It's also 2. And the limit as x approaches 3 of f of x is equal to f of 3. So, yes, it is continuous at x equals 3. And that's the 3-point definition of continuity at a point, right? The function has to exist, the limit has to exist, and those two things have to be equal to each other. And they gave you 2 points for this. 1 for saying yes, and for, with the little explanation that the one-sided limits are equal to each other as the other points. All right, so we had to have all of these things here to get both those points. In part B, it wants us to find the average value of f of x on the closed interval 0 to 5. So the average value of a function is just 1 over b minus a times the integral from a to b of the function. But in order to do that, we have to split this into 2 pieces. One's going to be the integral from 0 to 3 of root x plus 1, and the other will be the integral from 3 to 5 of 5 minus x. But we got to make sure we still have that 1/5 all the way out in front. Well, the integral of root x plus 1, that's one of those real easy u substitutions where if u is x plus 1, du is just dx, and you don't really even have to think about the u sub. Just treat it like it's u to the 1/2. So it becomes u to the 3/2 divided by 3/2, or 2/3 of u to the 3/2, 2/3 of x plus 1 to the 3/2. And we're going to evaluate that part from 0 to 3. And then we'll add to it the integral of 5 minus x, which is 5x minus x squared over 2, evaluated from 3 to 5. So we've got 1/5, and then now we'll plug in 3. So 3 plus 1 is 4, right? The square root of 4 is 2, and 2 cubed is 8. So it's 8 times 2/3, so 16/3. And then minus when we plug in 0. 0 plus 1 is 1. 1 to the 3/2 is 1. And multiply it by 2/3. So 2/3. And then we'll add to that what we get when we plug in 5 to this other one. So 5 times 5 is 25. Right? And 25 minus 25 halves is just going to be 25 halves. And then we'll have to subtract what we get when we plug in 3, which is 15. Right, minus 9 halves. 15 is 30 halves. So 30 halves minus 9 halves is going to be 21 halves. And now we can just go through and do the arithmetic here. 16, well, we got 1/5. And we have 16/3 minus 2/3 is going to be 14/3. And 25 halves minus 21 halves is going to be 4 halves. So that's just plus 2. 2 would be 6/3. So this is 1/5 of 20/3. Well, 20 over 5 is 4. So we just end up with 4/3. And they gave you 4 points for that. 1 for splitting it up here into the 2 different integrals. 1 for the antiderivative of root x plus 1. 1 for the antiderivative of 5 minus x. And 1 for correctly evaluating to get 4/3. And in part C here, we've got a new function g of x. where g of x is k root x plus 1 from 0 to 3, and mx plus 2 from 3 to 5, k and m being constants, it says g is differentiable at x equals 3. What are the values of k and m? So we know that we are going to need to figure out if this is continuous, right? We got to find when it's continuous because it says it's differentiable, so it must be continuous. So first, we'll do a limit as x approaches 3 from the left of g of x, which will be k times root 3 plus 1. So 3 plus 1 is 4, and the square root of that is 2. So that's 2k. And the limit as x approaches 3 from the right of g of x, we'll just need to plug in 3 to that. So that's going to give us 3m plus 2. So we want 2k to equal 3m plus 2. Now we also have to make the derivatives match up, right? So we'll do that here. G prime of x is going to equal, well, the derivative of k root x plus 1. The k is just a constant, so it'll just be a k. And then times the derivative of root x plus 1 is 1 over 2 root x plus 1, if x is between 0 and 3. And then the derivative of mx plus 2 is just m. So it's m if we're between 3 and 5. And we need those to equal each other at 3. So we need k over 2 times 3 plus 1 square root, which is just going to be 4. We need k over 4 to equal m. So now we just need to make all of this match up, right? This is just a system of equations here, right? We have k is equal to 4m. So if I plug in 4m here, we have 2 times 4m is equal to 3m plus 2, or 8m equals 3m plus 2, or 5m equals 2. So m must be 2/5. And if m is 2/5, then k is equal to 4 times 2/5, which is 8/5. And those are our values of m and k. And they gave you 3 points for that. 1 for setting 2k equal to m plus 2, 1 for getting k over 4 equals m, and 1 for solving the system to get the final answer. And that's the end of this function FRQ, which was question number 6 from the 2003 AP Calculus AB exam. All right, this is question number 4 from the 2004 AP Calculus AB exam. This is a function FRQ, where we're given the curve x squared plus 4y squared equals 7 plus 3xy. And we're asked to show that dy dx equals that expression 3y minus 2x over 8y minus 3x. So we'll take the derivative of our original curve with respect to x, right, which we have to do implicitly because it's got x and y terms in it. So the derivative of x squared with respect to x is just 2x. And the derivative of 4y squared with respect to x, we first take the derivative of it with respect to y, and then multiply by dy dx. So 8y dy dx. The derivative of 7 is 0. And then the 3xy will have 3x times the derivative of y with respect to x. And then plus the derivative of 3x, which is just 3 times y. And now we will get all of our dy dx terms to one side and all our other terms to the other side. So we'll have 8y dy dx minus 3x dy dx on the left equals 3y minus 2x. We'll factor out our dy dx, giving us dy dx times 8y minus 3x equals 3y minus 2x. And then we'll divide both sides by 8y minus 3x. And that completes the verification that that's the derivative. They gave you 2 points. 1 just for doing the original implicit differentiation correctly, and 1 for showing the algebra steps to verify that it was what they said it was. In part B, it says show that there is a point with x coordinate 3 at which the line tangent to the curve P is horizontal, and then find the y coordinate of P. So we've got we want dy dx to equal 0, which would be when 3y minus 2x, the numerator of that derivative, is equal to 0. And so we know that when x is 3, we get 3y minus 2 times 3 is equal to 0. Or if we add the 6 to the right-hand side, we get 3y is 6, or y would be 2. So the y coordinate we're talking about here is y equals 2. But we also have to verify that that point is actually on this curve. Right? We can't just assume that it is. So we'll do 3 squared plus 4 times 2 squared equals 7 plus 3 times 3 times 2. And 3 squared is 9. So we got 9 plus 16 here is equal to 7 plus 18, which is true. So that point is on the curve. And so we've shown that it's horizontal, a horizontal tangent line there. We found the y value, and we verified that it was on the function, or on the original equation. So that should be sufficient work there to earn those 3 points. 1 for just setting dy dx equal to 0. 1 showing that the slope is 0 when y is 2. And 1 for showing that the point is on the curve. And in part C, they ask us to find the value of the second derivative at that point that we just found, and then use that to determine if the curve had a local max, min, or neither at point P. So we have to find the second derivative here. So we're going to just note from the beginning, we had that dy dx. It was equal to 3y minus 2x over 8y minus 3x. And actually, let's just evaluate this right now at the point 3, 2. Well, we know what it is, right? We know that it equals 0 there, right? So now we'll do our derivative of dy dx, right? Our second derivative. And when we do that, we have to use the quotient rule. It'll be the denominator times the derivative of the numerator, which is going to be 3 dy dx minus 2, and then minus 3y minus 2x, and then the derivative of 8y minus 3x will be 8 dy dx minus 3, all over 8y minus 3x squared. Now, we know already that dy dx, all of our dy dx terms are just zeros. And also, we know that 3y minus 2x is also equal to 0. So anytime I see 3y minus 2x or a dy dx, I can just replace it with 0. All the other x's will be 3's, and all the other y's will be 2's. So at the point 3, 2, if y is 2, we have 16 minus, and if x is 3, 16 minus 9 there. And then dy dx we know is 0, so this is just negative 2. And then minus, well, we know that 3y minus 2x is 0, which means that 0 times anything is 0. So that's just 0. And we just said that 8y minus 3x, right, was 16 minus 9. And we'll square that. And so we can see that, one of the 16 minus 9's in the denominator will cancel with the one in the numerator, and we just have negative 2 over 16 minus 9, which is 7. And so we just end up getting negative 2/7. And we'll note that negative 2/7 is less than 0. And if the second derivative is less than 0, then the function must be concave down. And if a function is concave down at a place where its derivative is 0, that must have been a local maximum. And that gets you all 4 points. You got 2 points for the correct second derivative expression, 1 point for negative 2/7, and 1 point for the fact that it was a local maximum because the second derivative was negative, making the function concave down. And that's the end of this function FRQ. Is question number 4 from the 2004 AP Calculus AB exam. All right, this is question number 4 from the 2005 AP Calculus AB exam. This is a function FRQ. We've got a function f that's continuous from 0 to 4, and it's twice differentiable except at x equals 2. And f and its derivatives have all the properties shown in the table, and we can see that where it says d and e, that means that the derivatives of f prime and f double prime don't exist at x equals 2. And for 0 to 4, we want to find all values of x when f has a relative extrema. And we want to then determine whether it's a max or a min at those values and justify our answer. So the only place we can have a max or a min is if the derivative is 0 or undefined. So our derivative is 0 and our derivative is undefined at x equals 1 and x equals 2. And so we can see, though, that at x equals 1, f prime does not change signs. And so no max or min. Right? Because it started out as positive and was still positive afterward. But at x equals 2, f prime does not exist. And f prime changes from positive to negative. And if the derivative goes from positive to negative, the function goes from increasing to decreasing. So we have a max, we'll call it a relative maximum, at x equals 2. And they gave you 2 points for that. 1 for that there was 1 at 2, and 1 for your justification that it was a maximum. In part B here, they're asking us to sketch a graph of the function that has all of these characteristics. They don't really ask this much anymore, but we'll sketch a little graph anyway, just so we have an idea of what it looks like. We know that at x equals 0, the function's value is -1. Right? We also know that at x equals 1, its value is 0. And we know that at x equals 2, its value is 2. And that x equals 3, its value is back to being 0. So we know we're going to have these. That was not 3. At x equals 3, the value is 0. And so we also know that f prime was positive all the way till we got to 2, and then negative after that. So we need to be increasing and then decreasing. So we're going to increase, right, from 0 to 2, and then we're going to decrease from 2 to 4. And then we are going to be concave, it looks like concave down from 0 to 1, but then concave up from 1 to 2. So we're going to look something like increasing concave down, increasing concave up. And then we have a local maximum there at 2. And then we're going to be concave down, followed by concave up. So concave down and then concave up. And it's going to look something like that. And that would get you 2 points there. They gave you 1 point just for having the correct points, all those 4 points that I marked to begin with, and the correct in behavior. And then they gave you another point for the increasing, decreasing, and the concavity. All right, 1 more point for that. In part C, we've got g defined by g of x as the integral from 1 to x of f of t. We want to find all values of x when g has relative extrema. So g prime is equal to just f of x, right? And so we want to know, when does f of x equal 0, or when is it undefined? Well, it's never undefined, but it does equal 0 at 1 and at 3. And we can see that at x equals 1, it switches from negative to positive. And at x equals 3, it switches from positive to negative. So we're going to say x equals 1, and we'll say g prime goes from negative to positive. So that one is going to be a minimum. And at x equals 3, g prime goes from positive to negative, and therefore that is going to be a maximum. And they gave you 3 points for that. 1 for noting that g prime was f, and then 1 for the 2 critical points, and 1 for the 2 explanations. And here in part D, it says for that function g before, we want to know when does g have a point of inflection. And so, well, we know that g prime of x was f of x, which means that g double prime of x is f prime of x. And so we want to see when does f prime of x change signs. Well, f prime of x changes signs. Well, let's see here. It's positive, positive, negative, negative. So it changes signs at x equals 2. And that is our only place where we can have a point of inflection, is when the second derivative changes signs. Note that it is when the second derivative is non-existent, but that's okay. All that matters is it's either doesn't exist or is 0, and that it changes signs there. And so they gave you 2 points for that. 1 for the value x equals 2, and 1 for noting that that's where g double prime, which is f prime, changes signs. And that's the end of this function FRQ. It was question number 4 from the 2005 AP Calculus AB exam. All right, this is question number 5 from the 2005 Form B AP Calculus AB exam. It's a function FRQ, where we're given the curve y squared equals 2 plus xy. And we just first want to show that dy dx is y over 2y minus x. So we'll use implicit differentiation. We'll differentiate this curve with respect to x. So whenever we take the derivative of a y term, we'll attach a dy dx to it. So we get 2y dy dx is equal to, the derivative of 2 is 1. So the derivative of 2 is 0. And then we'll just take the derivative of xy using the product rule. So that'll be x times the derivative of y plus the derivative of x, which is 1 times y. And now we'll just get all the dy dx's to the left side here. Factor out the dy dx. And divide. And that should be a pretty straightforward part A. They gave you 2 points for it. 1 for doing the implicit differentiation correctly, and 1 for verifying that it equals what they said it did. In part B, it says to find all points x, y on the curve where the tangent to the curve has a slope of 1/2. So what we want to do is we want to just set our derivative, which was y over 2y minus x, equal to 1/2. And so we'll just cross multiply here, getting 2y is equal to 2y minus x. And effectively, that just tells us if we subtract 2y from both sides that 0 is equal to the opposite of x, or just x is equal to 0. So we have a slope of 1/2 whenever x is equal to 0. So we'll just go and take 0 and plug it back in up here to get y squared equals 2 plus 0. And square root to get plus or minus root 2. So our points are 0, root 2, and 0, negative root 2. And that was worth 2 points. 1 for setting it equal to 1/2, and 1 for getting the 2 points. In part C, it says show that there are no points on the curve where the line tangent is horizontal. Well, for the tangent line to be horizontal, we would need dy dx to equal 0. which is in the numerator of our derivative, and the numerator of our derivative is y, so that'd be when y is equal to 0. And so if we plug in 0 up here, we'll get 0 is equal to 2 plus 0. Well, that is not true. And so there are no points on the curve where y is equal to 0. So no horizontal tangent line. And that's all you got to do for part C. They gave you 2 points for that. 1 point for getting y equals 0, and 1 point for an explanation with this, with a little bit of work here to back it up. And here in part D, it says x and y are now functions of time t related by that same equation, y squared equals 2 plus xy. And they're telling us that at t equals 5, the value of y is 3, and dy dt is 6, and we want to find the value of dx dt. So now we just need to take the derivative of this with respect to t. So it's still implicit differentiation, just this time with respect to t. So the derivative of y squared will be 2y, the derivative with respect to y, and then times dy dt. The derivative of 2 is still just 0. And then the derivative of xy will be x times the derivative of y with respect to t, plus y times the derivative of x with respect to t. And we have a lot of the things we need. We have y is 3, and we have dy dt is 6. But what we don't have is we don't have a value for x, right? So as we go through here, right, if we're plugging in 3 for y and 6 for dy dt, we don't have a value for x here. So we have everything else except for the dx dt, which is what we're looking for. So we just need to go back to our original equation. When y is 3, just plug that in, you get 9 is equal to 2 plus 3x. Subtract the 2, and you get x is 7/3. So we'll put in 7/3 there for x. And now we can just solve for dx dt. 2 times 3 is 6, times another 6 is 36. Over here, 6 over 3 is 2, times the 7 is 14. And if you subtract 36 minus 14, you'll get 22. So we have dx dt is equal to 22 over 3. And they gave you 3 points there for part D. 1 for solving for the x value here. 1 for using the implicit differentiation with respect to t correctly. And 1 for plugging it all in and getting 22/3. And that's the end of this function FRQ. It's question number 5 from the 2005 Form B AP Calculus AB exam. All right, this is question number 6 from the 2006 AP Calculus AB exam. It's a function FRQ. We're given a twice differentiable function f that's defined for all real numbers. And we know that f of 0 is 2, f prime of 0 is -4, and f double prime of 0 is 3. And it says that this function g, given by e to the ax plus f of x, for all real numbers where a is a constant, and we want to find g prime of 0 and g double prime of 0 in terms of a. So we'll start with g prime of x. G prime of x is just e to the ax, because the derivative of e to the ax is e to the ax, times the derivative of ax, which is just a, and then plus f prime of x. So that tells us that g prime of 0, the first thing it asks us to find, is just a times e to the 0, because a times 0 is going to be 0, plus f prime of 0. But we know f prime of 0 is -4, and e to the 0 is 1, so we get a minus 4. And then it asks us to find g double prime, so we'll first find g double prime of x. So that's going to be the derivative of a e to the ax. Well, a is just a constant, so we'll keep that out in front. And then the derivative of e to the ax is just e to the ax times a. Well, if I multiply a by a, we're going to get a squared. And then we'll get plus f double prime of x. So g double prime of 0, well, we'll just plug in 0 for x. Same thing that happened in the first one, we're going to end up with e to the 0, which is just 1. So we have a squared times 1, or just a squared. And then f double prime of 0 was 3. So we got a plus 3. And they gave us 4 points for this. 1 for an expression for g prime, 1 for g prime of 0, 1 for the expression for g double prime, and 1 for g double prime of 0. And in part B, they are giving us a different function h, which is cosine kx f of x, where k is a constant. And they want us to find h prime of x, and then write an equation for the line tangent to the graph of h at 0. So in order to write the equation of the line tangent to h at x equals 0, we need to find h of 0. So we'll do that first. That's going to be the cosine of 0 times f of 0. And the cosine of 0 is just 1, and f of 0 is 2. So that's just 2. So we know that the point we're talking about is the point 0, 2. And then we need to then find h prime of x to find the slope. Well, that's going to be a product rule question because it's a cosine of kx times f of x. So we'll start with cosine kx times the derivative of f, which is f prime of x. And then we'll add to that the derivative of cosine kx, which is going to be negative sine kx times the constant k, and then times f of x. And if we're looking for h prime of 0, well, that's going to be the cosine of 0 times f prime of 0. Well, we know f prime of 0 is negative 4, plus k times the sine of 0. Well, the sine of 0 is 0. So actually, everything on this whole side just turns into 0, and we just get a slope of 1 times negative 4, because the cosine of 0 is 1. So just get a slope of negative 4. And then we've got the y-intercept already given to us, so we might as well just use slope-intercept form. Y equals negative 4x plus 2. And part B there was worth 5 points. That's it, just parts A and B for this question. 2 points for getting the correct expression for h prime. 1 point for getting h prime of 0. 1 point for getting h of 0. And 1 point for the final answer. And that's the end of this function FRQ. It was question number 6 from the 2006 AP Calculus AB exam. All right, this is question number 2 from the 2006 Form B AP Calculus AB exam. It's a function FRQ. We're given a graph of f prime, and we're told that f is defined for x greater than or equal to 0. F of 0 is 5, and f prime is defined as e to the negative x over 4 times the sine of x squared. So we want to use the graph of f prime to determine whether the graph of f is concave up, concave down, or neither on the interval from 1.7 to 1.9. So we know that a function is concave up or concave down if the sine of f double prime is positive or negative, right? So we're looking for the sine of f double prime. Is it positive or is it negative? And so we know that we can determine whether the second derivative is positive or negative by looking at if f prime is increasing or decreasing, right? And so if we look at our graph from 1.7 to 1.9, which is somewhere in that range there, we can see that f prime is decreasing, which means its derivative, the second derivative, f double prime, must be negative. So we'll say f prime is decreasing, which means that f double prime is less than 0. So f is concave down. And that's all you got to write there for part A. They gave you 2 points. 1 for the actual answer that it's concave down, and 1 for the reason that f prime is decreasing, so f double prime is negative. In part B, it says on the interval from 0 to 3, find the value of x at which f has an absolute maximum. Well, f has an absolute maximum when f prime goes from positive to negative, right? Because then f is going from increasing to decreasing. And so we can see that that happens right here. That's the only place where it goes from positive to negative. And so we just need to graph f prime of x on our graphing calculator and see what that x-intercept is. So we'll go into our graphing calculator, and we could do it by hand if we want to, but since it's a calculator question, we might as well go ahead and graph it. So our function was e to the negative x over 4 times the sine of x squared. So we'll graph this. We're looking at the interval from 0 to 3. So I'm going to change my window. I'm going to hit window and put my x-min as 0 and my x-max as 3. We'll graph it again. And now we'll hit second trace, option number 2 for 0. And we're already a little bit to the left of where that intercept is. So we'll hit enter. And then we'll go over and we'll hit enter again. And we'll hit enter one more time and get 1.772. And so it looks like that is at x equals 1.772. Now, of course, we're also looking at endpoints, right? Because we're talking about an absolute maximum here, right? So we could also check, and we need to also check x equals 0 and x equals 3, right? So those are our only real possibilities. And so we just need to evaluate what the value of our function is at each of those. So that means that since we know that f of 0 is 5, that means that an actual equation for the function f of x should be the integral from 0 to x of f prime plus 5, right? That way, it satisfies that the derivative of f is f prime. And also, if I plug in 0 for x up here, then I get the integral from 0 to 0 of f prime plus 5, which equals 5, right? Because the integral from 0 to 0 of anything is 0. So we'll just evaluate f of 0, f of 3, and f of 5. So we know that f of 0 is 5, so we don't really need to do anything there. But f of 1.772, we can find that value. And I'm not gonna round that. I'm gonna add that 4539 that's on there to this. Okay. So now when I use this on my calculator, we're gonna go back to our main window here, and we'll do math, option number 9 there for 0. For our integral, we're going to go from 0 to that value that we just had, which I've totally forgotten, 1.7724539. And we'll just input our function here for f prime, right, which we can hit the VARS button just to the left of clear and go over to the second column and choose function. And then that's the function that we just graphed. So we can just put y1 in there. We don't have to retype the whole function. And it looks like we get 0.679 there. And then, of course, don't forget to add your 5 to it. So we get 5.679. So put that here. And then we also want to check this at 3. And so we'll go back here. And we could just, instead of having to retype everything, we can just do this. And then, of course, instead of typing in 1.772, we're just going to put in 3. And don't forget the plus 5. I'll even just type plus 5 here this time. And we get 5.579. And so we can see that the largest of those 3 values, which were our only possibilities, was the value at 1.772. So our absolute max is at 1.77245539. And of course, you could have also got the exact value of that, right? Because you could just see when sine of x squared is equal to 0, that value happens to be the square root of pi also. So you could have done that by hand to find that and then used your calculator to check the values, but either way is fine since it's a calculator question. They gave you 4 points here for this. One for identifying the candidates here, right? All these candidates, and you didn't actually have to identify 0 because 0 is a location of a minimum, but if you ignored 0, you would have at least needed to explain why. And then you got 3 points for this. So I have 1 for showing that 5.679 was greater than 5.579. Right there, right, showing that f of root pi was greater than f of 3, and 1 for the final answer. And here in part C, it says write an equation for the line tangent to the graph of f at x equals 2. So that means we need f of 2, and we need f prime of 2 in order to do that. Right? We need a point and we need a slope. So f of 2 is just the integral from 0 to 2 of f prime plus 5. And we'll let our calculator do that. We've already done a bunch of these. I'm just going to go back up to this one we just did previously. And now we just want the integral from 0 to 2. So f of 2 is going to be 5.623. And then f prime of 2, we can find that. We'll just go back to our graph here. And this is f prime with graph, so we're going to hit second trace and option 1 for value. And then we'll just type in a 2. And it'll tell us f prime of 2 is negative 0.459. And so now we'll just write the equation of our tangent line. It'll be y minus our y value of 5.623 equals our slope of negative 0.459 times x minus 2. And they gave you 4 points for this part. 2 points for having just the expression for f of 2, 1 for the value for f prime of 2, and 1 for the final answer. And that is the end of this function FRQ, question number 2 from the 2006 Form B AP Calculus AB exam. All right, this is question number 3 from the 2006 Form B AP Calculus AB exam. It's another function FRQ where we're given a graph of a function here, which models the height of a skateboard ramp. We know that at x equals 0, the value of the function is 0 and the slope is 0. At 4, we know the value of the function is 1 and the slope of the graph is 1. And between x equals 0 and x equals 4, the function is increasing. And we're saying f of x equals ax squared, where a is a non-zero constant. And it asks us to then show that it is not possible to find a value for a so that f meets requirement 2 that we had up there above. So what this is saying is that the value of the function at 1 is 4. So that means that f of 4 is equal to 1. And it also says that the slope of the graph of the function is 1. So that would mean that f prime of 4 would also need to equal 1. Right? So first of all, if f of 4 is equal to 1, right, then that means we have 1 is equal to 4a, or a would have to equal 1/4, right? Sorry, not 1/4. We're putting in 4 for x. So let's do that correctly. If we square 4 for ax squared, that would be 16a, and a will have to be 1/16. Over here, f prime of 4 is also supposed to equal 1. Well, f prime of x is 2ax, which means that 1 is supposed to equal 8a, or a would need to equal 1/8. And clearly 1/16 is not equal to 1/8, and therefore it can't meet those requirements. And you got 2 points there for that. One for getting either a equals 1/16 or a equals 1/8, and the second point was for finding the other one, showing that it cannot work. In part B, it says, let's let g of x equal cx cubed minus x squared over 16. C is a non-zero constant. Let's find the value of c so that g meets requirement number 2 again. So that means that this time g of 4 needs to equal 1, and g prime of 4 needs to equal 1. Right? So g of 4 is just going to be 4 cubed is 64, so 64c minus, and then if we square 4, that's 16 over 16, so 64c minus 1, or c will need to equal 2 over 64, which is 1/32. And so it seems like hopefully that's the right value here. G prime here is going to be, we'll write it out here, g prime of x is going to be 3cx squared minus 2x over 16, which will just be 1/8x. And so if we do g prime of 4, we should end up getting 4 squared is 16. 16 times 3 is 48, so we'll have 48c minus 1/8 of 4, so minus 1/2 should equal 1. Or 48c is equal to 3/2. We'll actually write 48. 48c is equal to 3/2. And if you multiply 48 by 2, you get 96, and divide that by 3, you get a 1/32 here. All right, so if we multiply by the 2 and then divide by that 96, we get 1/32. And so it looks like our answer is C equals 1/32. And it seems to work for both of them this time. So they gave you 1 point just for that work here in part B. In part C, it says use your function g and your value c from part B. Show that g does not meet requirement number 3. So our function g was cx cubed minus x squared over 16, and we got 1/32. So that'll be 1/32 x cubed minus x squared over 16. And we want to show that our function is increasing from 0 to 4. We'll show that it's not, actually. So let's find g prime of x. G prime of x will be 3/32 x squared minus 1/8 x. And if we set that equal to 0, we can factor out an x, leaving us with 3/32 x minus 1/8. And that's equal to 0. And x is 0. And also when 3/32 x minus 1/8 is equal to 0, or 3/32 x is equal to 1/8, or when x is equal to 4 over 3. And if we make a sign chart here with 0 and 4/3 on it, I think we can very clearly see that if we plug in something like 1 to our derivative, right, we end up with a positive for x, and 3/32 minus 1/8 is negative, right? That's 3/32 minus 4/32, which is going to be negative. And then something more than 4/3, like, I don't know, 1 million, or not a million. Let's cut it off at 4 because that's what we're supposed to use. Like plug in 3/32 minus 3/8 is, 9/32 minus 1/8. If you put in a 3 there, 9/32 minus 1/8 is clearly positive. But we can see that g prime is less than 0 on 0 to 4/3, so g is decreasing. And so we know that g is decreasing for a portion of this, and therefore it must not be increasing for all of 0 to 4. So you got 1 point for the expression for g prime and 1 point for showing that it was 0 on that interval from 0 to 4/3. in part D, it says let h of x equal x to the n over k, where k is a non-zero constant and n is a positive integer. We're going to find the values of k and n so that h meets requirement 2. So that means that we want h of 4 to equal 1, and we want h prime of 4 to equal 1 as well, just like before for requirement 2. So if h of 4 is equal to 1, then that means we have 1 equals 4 to the n over k. And then h prime of 4, well, the derivative of x to the n over k is just, we'll write this out. H prime of x is going to be equal to nx to the n minus 1, still over k. And so if I plug in 4 for x there, that's supposed to equal 1 as well. So we'll do that over here. If I plug in 4 for x, we get 1 equals n times 4 to the n minus 1 over k. And since both n times 4 to the n minus 1 and 4 to the n over k are both supposed to equal 1, right, we should be able to figure out if we set those equal to each other, right, we'll end up with 4 to the n over k is equal to n times 4 to the n minus 1 over k. We can just multiply both sides by the k, or really we can just think about that k doesn't really, that value of k here doesn't really matter. We need to figure out what n is going to be first. So we need that 4 to the n is equal to n times 4 to the n minus 1. Well, if you divide both sides by 4 to the n minus 1, you can see if I do 4 to the n divided by 4 to the n minus 1, you need to subtract the exponents, right? So n minus the quantity n minus 1 is just n. Sorry, it's just 1. So we end up with 4 to the first power is equal to n. So now we know that n is equal to 4, right? This side, it cancels. And if I do n minus 1 as the subtraction of the exponents, since they have the same base, that's just equal to 1. So it's 4 to the first power is equal to n. So n is 4. And once we know that n is 4, we should be able to figure out what k is equal to. Just plug it into either one of the original equations, right? Here we have k equals 4 to the n, so 4 to the 4th. So k must be 256. So we've got a k value and we've got an n value. And we're completely out of room here, but we can now rewrite our function. Our function is going to be x to the 4th over 256. So we've got h of x is equal to x to the 4th over 256. And so requirement 1 was that at x equals 0, the function's value is 0 and the slope was 0. So h of 0 is clearly 0. And h prime of x, well, we can now see that that's 4x cubed over 256. 4 over 256 is 1 over 64. So it's x cubed over 64. So h prime of 0 is also 0. So that proves requirement 1. And then if we look back, requirement 3 was that from x equals 0 to x equals 4, the function had to be increasing, right? And so if we know that h prime of x is equal to x cubed over 64, that is definitely greater than 0 for 0 to 4. It's greater than 0 for all positive values of x. And so since h prime of x is greater than 0, that means h is increasing. Right, so that proves requirement number 3. And they gave you 4 points there for that. They gave you, let's see, we'll go back here. They gave us first 1 point for just setting 4 to the n over k equal to 1. They gave us 1 point for this other one, n times 4 to the n minus 1 over k equal to 1. 1 point for getting both the values of k and n, and then 1 point for all the work on the second page that we had, all that verification. And that is the end of this function FRQ. It was question number 3 from the 2006 Form B AP Calculus AB exam. All right, this is question number 3 from the 2007 AP Calculus AB exam. It's a function FRQ, where we're given two functions, f and g, which are differentiable for all real numbers, with g strictly increasing. And we got values of both f, g, and their first derivatives in the chart. We're also given this other function h, which is f of g minus 6. And we want to explain why there's a value on the interval 1 to 3, such that h of r is equal to -5. Well, what we need to start with here is just thinking it's probably going to be an intermediate value theorem question, right? Because they give us an interval and say, when does the function equal that? So let's find h of 1 and h of 3. H of 1 will just be f of g of 1 minus 6. So f of g of 1, well, g of 1 is 2, so this will be f of 2 minus 6. And f of 2 is 9, so this will be 9 minus 6, which is just 3. And then we'll look for h of 3, which is f of g of 3 minus 6, which will be f of 4, because g of 3 is 4, minus 6. And f of 4 is -1, so this will be -1 minus 6, which is -7. And we can see that -7 is less than -5, and 3 is more than -5. So we'll note that h is continuous because f and g are continuous. And we'll also note that -7 is less than -5, which is less than 3, right? So h of r must equal -5 on the interval from 1 to 3, because h of 1 was 3 and h of 3 was -7. And the reason will be our intermediate value theorem. And you're going to get 2 points for this. 1 just for getting the values, and 1 for the correct conclusion using the intermediate value theorem. Here in part B, it asks us to explain why there must be a value on the interval 1 to 3 such that the derivative of h is equal to -5. And so in order to figure that out, we need to find the average rate of change of h on that interval from 1 to 3. So we need to do h of 3 minus h of 1 over 3 minus 1, right? And well, we just found h of 3, right? H of 3 was -7, and h of 1 was 3. So we have -7 minus 3 over 2, which equals -5. And we'll note, and h is continuous, which we already stated why in the last one, and differentiable, because a composition of two differentiable functions is also differentiable. So mean value theorem must apply, right? The average rate of change must equal the instantaneous rate of change, which is h prime of c. And you got 2 points for this one, 1 for the average rate of change and 1 for the conclusion using the mean value theorem. In part C, it says w is now the function, the integral from 1 to g of x of f of t dt. Find the value of w prime of 3. So we want the derivative of this integral from a constant to a function of another function. So w prime of x, the derivative of an integral from a constant to a function is just the inside function there, f, evaluated at the g of x function, the one that's in the upper limit, and then we need to multiply that by the derivative of g. And we just want w prime of 3, so w prime of 3 will be f of g of 3 times g prime of 3. And g of 3 is 4, so this will be f of 4 times g prime of 3, which is 2. And f of 4 was -1, so this is -1 times 2, which is -5. 2. And they gave you 2 points for this, 1 for properly using the chain rule there, and 1 for the correct final answer. Here in part D, we're talking about the inverse of g, and we want the equation of the tangent line to the inverse of g at x equals 2. So what we need to do is we need to say, well, if g and its inverse are what we're looking at here, and we want g inverse to have a point that is 2 comma something, then g must have a point that is something comma 2. So we'll look for when does g of x equal 2? That's when x equals 1. So the value of g, the point there that we're talking about is 1, 2. With g inverse, we're talking about the point 2, 1. And the inverse rule says that if we want g inverse prime at 2, that should be 1 over g prime of 1. Well, g prime of 1 is 5, so this should be just 1 over 5. So now we have the slope and the point, so we should just do y minus our y value of 1 equals 1/5, our slope, times x minus our x value of 2. And that ought to be all we need to do there. For part D, we get 3 points for that. You got 1 point for finding g inverse of 2, so getting 1 there. 1 point for the slope, and 1 point for the final tangent line. And that's the end of this function FRQs question number 3 from the 2007 AP Calculus AB exam. All right, this is question number 6 from the 2007 AP Calculus AB exam. This is a function FRQ where we're given the function f of x equals k root x minus ln x for x greater than 0, where k is a positive constant. And first it just asks us to find f prime and f double prime. So f prime of x, well, the derivative of a constant times root x is just the constant over 2 root x. And then the derivative of ln x is 1 over x. And then f double prime of x, well, this is, if we maybe rewrite these a little bit, k over 2 x to the 1/2, or sorry, x to the negative 1/2, minus x to the negative 1. So if it helps us to look at them this way, we can now use the power rule, right? It now becomes negative k over 4x to the negative 3/2. And then minus 1 times the minus 1 in front gives us a plus x to the negative 2. And they just gave you 1 point for each of these functions, the derivative and the second derivative. In part B, it asks us for what value of the constant k does f have a critical point at x equals 1, and then determine min max, or neither at that critical value. So f prime of 1, right, we had k over 2 root x, so that'll be just k over 2, and then minus 1 over 1, so that'll just be minus 1. And we want this to equal 0, so we can see that that equals 0 when k over 2 is equal to 1, or when k is equal to 2. And we know that we can also evaluate our second derivative here. This is a place where the derivative equals 0, so our second derivative at 1, whether it's positive or negative, should tell us if this is a max, a min, or neither. So our second derivative at 1, if we evaluate that, right, it was negative 1/4 of k, so negative 1/4 of 2, times x to the 3/2, so 1 to the 3/2 is just 1, and then it was plus x to the negative 2, so plus 1 to the negative 2, which is just 1. So looks like we end up with negative 1/2 plus 1, which is positive 1/2. And so we'll note that that's greater than 0, and since that's greater than 0, the function must be concave up, which means that it must be a local minimum. And we can maybe say, we'll say local minimum by second derivative test, because they want you to justify your answer. So at least say what the test is called. They gave you 4 points there, 1 for just setting it equal to 0, 1 for getting the value of k, 1 for the answer of minimum, and 1 for the work to show why it was a minimum. And for part C, it says, for a certain value of the constant k, the graph of x, or graph of f, has a point of inflection on the x-axis. So find the value of this. So if we're on the x-axis, that means that the y value must equal 0. So we want f, first of all, we want f double prime of x to equal 0. But we want that to happen also when f of x is equal to 0. And so, right, because we want to be on the x-axis. So when does f of x equal 0? Well, f of x equals 0 at the k value. Right, so we have k, we'll say k root x minus ln x is equal to 0. So that'd be k root x equals ln x, or k is the natural log of x over root x. And for f double prime of x equal to 0, we had negative 1/4 k x to the negative 3/2 plus 1 over x squared, or plus x to the negative 2. And we want that to equal 0. So we'll add the 1/4 k to the other side there. So we'll have 1 over x squared equals 1 over 4, or we'll have k over 4 x to the 3/2, which gives us k, if we cross multiply here, we'll get k is equal to 4x to the 3/2 over x squared, which is just 4 over root x, right? And so we just need to set these two k values together to see what x value makes them both true. So we'll do 4 over root x equals ln x over root x. Obviously, the root x's there don't really matter. We can just say 4 is equal to ln x, or x is, that means x is equal to e to the 4th power, right? And we are asked, right, to find the value of k. So that means we're going to just plug that back into either one of these. It doesn't matter which one, right? Because we'll get the same thing. We'll get k is equal to 4 over the square root of e to the 4th. Well, the square root of e to the 4th is e squared. And they gave you 3 points here for that. 1 point for setting either f double prime of x equal to 0 or f of x equal to 0. 1 point for getting this equation here in one variable, and 1 point for the final answer. And that's the end of this function FRQs, question number 6 from the 2007 AP Calculus AB exam. All right, this is question number 6 from the 2007 Form B AP Calculus AB exam. It's a function FRQ where we're given f, which is a twice differentiable function, such that f of 2 is 5 and f of 5 is 2, and that g is f of x. And then it asks us first, explain why there must be a value c on 2 to 5, such that f prime of c equals -1. Well, if we're talking about the derivative of f and we're just given values of f, the mean value theorem is what makes sense, right? We can say that f is continuous because it's differentiable. And we know that the value of f of 5 minus f of 2 over 2 minus 5, right? The average rate of change, which is f of 5 is 2 and f of 2 is 5. So it's 2 minus 5 over -3. Sorry, over positive 3. I was already doing the 2 minus 5 there. So -3 over 3 gives us -1. And so by the mean value theorem, that means f prime of c must equal -1, right? The instantaneous rate of change must equal the average rate of change somewhere on the interval from 2 to 5. And they gave you 2 points for that. 1 just for getting this average rate of change, and 1 for the conclusion using the mean value theorem. In part B, it says, show that g prime of 2 equals g prime of 5, and then do some other stuff first. So let's first we'll show that g prime of 2 is g prime of 5. So g prime of x is the derivative of f of x. So we take the derivative of the outer function, which is this outer f, so f prime, evaluated at the inner function, f of x, and then multiply by f prime of x. So we know that that's g prime. So we can find g prime of 2. G prime of 2 ought to be f prime of f of 2 times f prime of 2. And so f of 2 we know is 5. So now we have this is equal to f prime of 5 times f prime of 2. And then if we look at g prime of 5, right, we can't really do anything else with that because we don't know the values of f prime of 5 and f prime of 2. But we can find g prime of 5 and see if it looks the same as that. That's going to be f prime of f of 5 times f prime of 5. And we know that f of 5 is 2, so this becomes f prime of 2 times f prime of 5. And obviously, those are equal to each other, right? So g prime of 2 equals g prime of 5. And we know that f is twice differentiable, and g is just a composition then of two twice differentiable functions. So therefore, g is differentiable and also continuous. It must be continuous if it's differentiable. And so we can again use the mean value theorem. And we'll maybe make a note just because f is differentiable. In fact, it is twice differentiable. And so therefore, that means that if g prime of 5 minus g prime of 2 over 5 minus 2 equals 0, which it does because g prime of 5 and g prime of 2 are equal to each other. So by the mean value theorem, once again, that means that its derivative, g double prime at some value k equals 0, somewhere on 2 to 5. And they gave you 3 points this time, 1 for the expression for g prime, 1 for showing that they're equal, and 1 for the conclusion, once again, using the mean value theorem. In part C, it says, show that if f double prime of x equals 0 for all x, then the graph of g does not have a point of inflection. Well, points of inflection occur when the second derivative equals 0 or when it's undefined, right? And so if I find the second derivative of g, right, we know that that's just the derivative of g prime of x, right? And we had g prime already, right? G prime, I'll write g prime up here. G prime was f prime of f of x times f prime of x. So to find the derivative there, we just have to use the product rule, right? So that'll be the derivative of f prime of f of x times f prime of x. That'll give us f prime of f of x times the derivative of f prime, which is f double prime, and then plus the derivative of f prime of f of x, which will be f double prime of f of x times f prime of x, and then times another f prime of x. Well, we know that f double prime for any value is equal to 0, which means that for any x value that I plug in here, this is going to equal 0, and this is going to equal 0, because f of x, when I evaluate to find f of x, it's just some number, and then f double prime of that has to be 0. So that tells us that g double prime of x must also equal 0 for all x. Therefore, g double prime cannot change signs. And cannot have a point of inflection. And they gave you 2 points for that. One, just for considering g double prime at all. right? Finding the value there. And then second for showing that it was equal to 0 for all x. And here in part D, we've got a new function h of x, which is f of x minus x. And we want to explain why there must be a value r on 2 to 5 such that h of r is equal to 0. Well, first let's see what h of 5 is. So h of 5 is going to be 2 minus 5, which is negative 3. And then we'll see what h of 2 is. Right? Well, h of 2 is just going to be 5 minus 2, which is 3. And we can see that there's a sign change between h of 2 and h of 5. Right? We go from positive at h of 2 to negative at h of 5. And we'll say since h is continuous, which we know it's continuous because f was continuous, and if we just subtract another continuous function, it must be continuous, the intermediate value theorem applies. And h of r must equal 0 on 2 to 5 because h of 5 is less than 0 and h of 2 is greater than 0, right? We have a sign change there. And they gave you 2 points for that, 1 for finding those values and 1 for the conclusion using the intermediate value theorem. And that is the end of this function FRQs, question number 6 from the 2007 Form B AP Calculus AB exam. All right, this is question number 6 from the 2008 AP Calculus AB exam. This is a function FRQ. We got f is the function given by ln x over x for all x greater than 0. And the derivative, f prime, is 1 minus ln x over x squared. They want us to write an equation for the tangent line to f at e squared. Which means first we need to find f of e squared. Then we need to find f prime of e squared. So f of e squared is just the natural log of e squared over e squared. Right? And of course, the natural log of e squared, that 2 can come out in front. So 2 ln e is just 2 times 1 over e squared. And then to find f prime of e squared, we'll just do 1 minus the natural log of e squared over e squared squared. And again, we just said the natural log of e squared is 2, so this is 1 minus 2 over e to the 4th, or negative 1 over e to the 4th. So we'll just write our tangent line equation, y minus our y value of 2 over e squared equals our slope of negative 1 over e to the 4th times x minus e squared. And that is our tangent line equation, and they gave you 2 points for it, 1 for getting both f and f prime, and 1 for the equation. In part B, it asks us to find the x-coordinate of the critical point of f, and then determine if it's a min, max, or neither. So when does f prime equal 0? Well, that'd be when 1 minus ln x equals 0. We've also looked for when it's undefined, but it's only undefined if x squared is 0, which isn't in our domain, right? X can't be 0. So this just gives us 1 equals ln x, or x is equal to e, right? Just know that ln of e is 1, or exponentiate both sides to clear out the natural log. Right, so our x-coordinate of our critical point of f is at e, and we know we can just make a sign chart here. Even though a sign chart is not sufficient justification, we can at least make one to see what's going on. If I plug in something between 0 and e, like 1, if I plug in something like 1 into my derivative, right, we get 1 minus the ln of 1, right, which is 1 minus 0, or just 1, over 1 squared. So we get a positive value here. And if I plug in something more than e, like 1,000,000, right, we get a negative value here. So we can say that f prime, if x is greater than 0 on 0 to e, f prime of x less than 0 on e to infinity. So x equals e is a relative And if our function increases then decreases, that means it's a relative maximum. And they gave you 3 points there. 1 for getting E, 1 for saying maximum, and 1 for a justification. In part C, it says the graph of f has exactly 1 point of inflection. Find the x-coordinate of it. That means we need a second derivative to find when we have a point of inflection. So we'll use the quotient rule, the denominator, times the derivative of the numerator, which derivative of 1 is 0, and derivative of negative ln x is negative 1 over x, and then minus the numerator times the derivative of the denominator all over the denominator squared. We could simplify this a little to get negative x, and then minus 2x, and then plus 2x ln x, it looks like, in the numerator there, and then all over x squared. Well, these all divide by x, and I can combine a negative 1 with the negative 2, right? So that's negative 3 plus 2 ln x all just over x. Right? If I negative x minus 2x is negative 3x, and then if I divide the negative 3x and the 2x ln x by one of the x's in the denominator, we should get negative 3 plus 2 ln x. Oh, this should have been squared. So really, this should be x to the 4th down here. Don't screw up your quotient rule like that. So really now this is an x cubed. But that is kind of beside the point, because the only thing that makes this undefined is x equals 0, which isn't in there. So we want to see when is this equal to 0. And that'd be when negative 3 plus 2 ln x equals 0, which means that ln x is going to equal 3 over 2, or x is equal to e to the 3/2. And we should indicate, right, we should make a little sign chart here, right? And then we'll put e to the 3/2 on it. So if I put in, let's say, e to this, right, we get negative 3 plus 2 ln e over x cubed, or over e cubed, which negative 3 plus 2 is still negative 1, so this is less than 0. So we're negative here. And if I put in something more than e to the 3/2, we'll find that it's positive. So we'll note that f double prime of x is less than 0 on 0 to e to the 3/2. F double prime of x greater than 0 on e to the 3/2 to infinity. So x equals 3/2 is the location of our point of inflection. 3 points there, 2 points for the correct second derivative, and 1 point for the answer with the justification that it changes, the second derivative changes signs at e to the 3/2. So that's where our point of inflection is. And here in part D, it wants us to find the limit as x approaches 0 of f of x, right? And so 0 from the right of f of x. So if we think about this, well, we've got the natural log of 0 from the right-hand side divided by 0 from the right-hand side. Well, if we think about the natural log of 0 as we approach from the right, we're going down towards negative infinity. So this is negative infinity divided by a very small positive number. And that, of course, is just going to make that an even larger negative. So this is equal to negative infinity. Or, of course, since we know that if it equals an infinite value, we can also say this does not exist. So either negative infinity or does not exist would be an acceptable answer to get the 1 point there for part D. And that is the end of this function FRQ, which was question number 6 from the 2008 AP Calculus AB exam. All right, this is question number 4 from the 2008 Form B AP Calculus AB exam. This is a function FRQ where we're given 2 functions, f and g. F is the integral from 0 to 3x of root 4 plus t squared dt. And g of x is f of sine x. So first, let's find f prime of x, right? So f prime of x, well, that's just the derivative of an integral from a constant to a function, 0 to 3x, of some other function. So the fundamental theorem of calculus says plug in the 3x as t, so it's root 4 plus t squared, and then multiply by the derivative of the 3x. So we're going to get 3 root 4 plus 9x squared as f prime of x. And then to find g prime of x, well, g prime of x is just a chain rule problem, right? It's f of sine x, so it should be f prime, derivative of the outer function, evaluated at the inner function, times the derivative of the inner function. Well, f prime of sine x is just going to be 3 root 4 plus 9 sine squared x, and then times cosine of x. And they gave you 4 points here for that. 2 points for f prime and 2 points for g prime. In part B, they want us to write the equation of a line tangent to g at x equals pi. So we need to find g of pi. G of pi will be f of sine pi. And we know that the sine of pi is 0. So that's just f of 0, which is the integral from 0 to 0 of 4 plus root 4 plus t squared. Well, the integral from 0 to 0 of anything is just 0. So we know that g of pi is 0, which means that we're looking at the point pi comma 0. And then we also need to find g prime of pi. And we just found g prime, right? G prime was 3 root 4 plus 9 sine squared x, so 9 sine squared pi, times the cosine of pi. And we know that the sine of pi is 0, so this is just a square root of 4 plus 0, or square root of 4 inside of here. So 3 times 2, which is 6, times the cosine of pi. The cosine of pi is -1. So g prime of pi is -6. So our equation should be y minus 0 equals our slope of -6 times x minus pi. And that's our answer for part B. They gave you 2 points there. 1 if you found either g of pi or g prime of pi, and 1 for having the actual equation with the correct values for both of them. And here in part C, it says write but don't evaluate an integral expression that represents the maximum value of g on the interval from 0 to pi. And so first we have to figure out when we might actually have a maximum, right? So when does g prime of x equal 0? And as we already looked at before, right, g prime of x was 3 times, we'll write this all out, it's 3 times the square root of 4 plus 9 sine squared x times cosine. So 3 times the square root of 4 plus 9 sine squared x times cosine x. And the only way to make that 0 is if cosine x is equal to 0, which would be x equals pi over 2. Or if 4 plus 9 sine squared x were to equal 0, but that would tell us that sine squared x is equal to -4/9, which never happens. So we know that we can have a max at x equals pi over 2, potentially. And we have to show that it's actually a maximum there, right? Well, we know 3 is positive, and we know whatever's inside this square root, when we square root it, we end up, it must be positive. And when we square root it, we're going to end up with a positive. So 3 root 4 plus 9 sine squared x, 9 sine squared x, is always greater than 0. And we'll say that cosine x changes from positive to negative at pi over 2. So the max of g is at pi over 2. So now we know that the max occurs at pi over 2, right? Because our derivative is going from positive to negative there, right? So now we just need an expression that finds what g of pi over 2 is, right? And so g of pi over 2 should just be f of the sine of pi over 2, and the sine of pi over 2 we know is 1. So that should just be f of 1, and f of 1 is equal to the integral from 0 to 1, or sorry, 0 to 3, it's 3x, of root 4 plus, you can put t squared dt, you can put x squared dt, put whatever you want there. It's just the integral from 0 to 3 of 4 plus root 4 plus t squared dt. They're going to give you 3 points there for that. 1 for just setting g prime equal to 0, 1 for justifying a max at pi over 2, and 1 for the final expression. And that is the end of this function FRQ. Question number 4 from the 2008 Form B AP Calculus AB exam. All right, this is question number 6 from the 2008 Form B AP Calculus AB exam. This is a function FRQ, and we've got a curve x squared plus 2x plus y to the fourth plus 4y equals 5. They want us to show that the derivative equals that expression that they gave us. So we'll just take the derivative of this implicitly with respect to x. So we get 2x plus 2 plus, when we take the derivative of y to the fourth with respect to x, we get 4y cubed times dy dx, right? The derivative of it with respect to y times dy dx. And then the same with the 4y, so plus 4 dy dx. And the derivative of 5 is 0. We'll move the 2x and the 2 to the other side, and when we do that, we'll also factor out the dy dx here. So we got 4y cubed plus 4. And over here, we'll have negative 2x minus 2. And now we can just divide. Dy dx is negative 2 times x plus 1. We might as well factor out the negative 2, right, since they did that. And then we'll divide by 4y cubed plus 4. And if I divide by that, we can factor out a 4 also. So that's going to be 4 times y cubed plus 1. And of course, the 2 over the 4 cancels to become just a 2 in the denominator. And we've got exactly what they wanted us to show that derivative was equal to. 1 point for correctly doing the implicit differentiation, and 1 point for fully verifying that that's what it equaled. In part B, they want us to write the equation for the tangent line to the curve at negative 2, 1. So we've got the point. We just need to evaluate dy dx at negative 2, 1. Dy dx was negative x plus 1. So our x value here is negative 2. And in our denominator, we had 2, and then we had y cubed plus 1, so y is 1, 1 cubed plus 1. Negative 2 plus 1 is negative 1, and negative 1 in the numerator is just going to be a 1. And then in our denominator, we've got 2 times 2, so a slope of 1/4. Our equation in point slope form will then just be y minus 1, right, our y value, equals our slope of 1/4 times x minus negative 2, or just x plus 2. And they gave you 2 points there. 1 for the slope and 1 for the equation. In part C, we're looking for the coordinates of the 2 points when the tangent to the curve is vertical. So we want dy dx to be undefined, and that happens when its denominator is equal to 0. Right, and so our denominator was 2 times y cubed plus 1. So we want, when does that equal 0? So that'd be when y cubed plus 1 equals 0, or when y cubed is negative 1, which means that y must be negative 1. So we're looking for the 2 points on the curve when y is equal to -1. We'll just plug -1 up here, and you get x squared plus 2x plus -1 to the 4th plus 4 times -1 equals 5. And we just need to solve this equation. So we have x squared plus 2x. -1 to the 4th is 1. And then that's going to be -4. So we have +1 minus 4, which is going to be -3 equals 5. And then we can just subtract the 5 over x squared plus 2x minus 8 equals 0. Factor and solve. And we get x plus 4 and x minus 2, giving us x equals -4 and x equals 2. So we can be pretty certain that the 2 points are -4, -1, and 2, -1. Now, what we should always check and make sure is that also our numerator, which was -x plus 1, does not equal 0, right? Because if we have 0 over 0, that does not work out. And if we plug in the x value of -4 or 2, neither of those make x plus 1 0. So these both work. And we got 3 points, 1 for getting y equals -1, 1 for just substituting that back in, and 1 for the 2 points. And here in part D, it asks, is it possible for this curve to have a horizontal tangent at points where it intersects the x-axis? Right, so we can have a horizontal tangent line, right? A horizontal tangent is going to be horizontal tangent if dy dx equals 0. So that'll be if the opposite of x plus 1 equals 0. That was the numerator of our derivative. So basically, if x equals -1, well, just plug x equals -1 back into your original equation, right? You get -1 squared plus 2 times -1 plus y to the 4th plus 4y equals 5, right? And so what we end up with here is 1 minus 2 plus y to the 4th plus 4y equals 5, or y to the 4th plus 4y. And then we've got 1 minus 2 is -1. And if we have -1 there, setting that equal to 5, right? Then we're sitting here looking at this now, saying, well, can it happen when it intersects the x-axis, right? So if it intersects the x-axis, that would be when y is equal to 0. So if y is equal to 0, then the y to the 4th and the 4y terms are just going to go away. And we just end up with -1 equals 5. So the only way for us to have this happen at the point -1, 0 is if -1 is equal to 5. So we could say no, it's not possible, because -1, 0 is not on the graph. Right? So we can only have a horizontal tangent when x equals -1, but the point -1, 0 doesn't lie on the graph. And they gave you 2 points here for this. One for testing it out with -1 and 0, right? So kind of doing both those things there. And 1 for a little explanation that says, no, that point's not on the graph. And that's the end of this function FRQs, question number 6 from the 2008 Form B AP Calculus AB exam. All right, this is question number 5 from the 2009 AP Calculus AB exam. This is a function FRQ. And we're given just a chart of values here of f of x. We're told that f is twice differentiable. And we want to estimate f prime of 4. So the best way to estimate f prime of 4 is just do the average rate of change on the interval from 3 to 5, the smallest interval surrounding it. So that'll be -2 minus 4 over 5 minus 3. Well, that's -6 over 2, which is just -3. So they're going to give you 1 point there for part A for finding that value. In part B, it asks us to evaluate the integral from 2 to 13 of 3 minus 5 times f prime of x. Well, the integral of 3 is just 3x. And the integral of 5f prime of x is 5f of x. So all we want to do is evaluate 3x minus 5f of x from 2 to 13. So, well, 3 times 13 is 39. And then minus 5 times f of 13. F of 13, if we look in the chart, is 6. And then we'll subtract from that. When we plug in 2, we get 3 times 2 is 6. Minus 5 times f of 2. And f of 2 is just 1, so minus 5 times 1. So we've got 39 minus 5 times 6. 39 minus 30 is 9. And then 6 minus 5 is 1, so we have 9 minus 1, which is just 8. They gave you 2 points here, 1 for correctly getting this integral using the fundamental theorem of calculus to integrate f prime to f, and 1 for the answer. In part C, they want us to use a left Riemann sum with the subintervals indicated to approximate the integral from 2 to 13 of f. So the first subinterval from 2 to 3, right, 3 to 2 is 1 unit, so 1 times the left endpoint of 1. And then from 3 to 5 is 2 units, so it'll be plus 2 times the left endpoint of 4. And then from 5 to 8 is 3 units times the left endpoint of -2. And from 8 to 13 is 5 units times the left endpoint there of 3. Just do the arithmetic there real quick. Let's see, we get 1 plus 8 is 9, minus 6 is 3, plus 15 is 18. And we got 2 points, 1 for the setup and 1 for the answer. Here in part D, it says, let's suppose f prime of 5 was 3, and that f double prime is negative from 5 to 8. We want to use the tangent line to show that the graph, the tangent line to f at 5 to show that f of 7 is less than or equal to 4, and the secant line on 5 to 8 to show that f of 7 is greater than or equal to 4/3. All right, well, that seems easy enough. We'll just write the equation of the tangent line of f at x equals 5. So we need f of 5, right? And f of 5 is -2, and f prime of 5 is 3. So our tangent line equation is going to be y minus -2, or y plus 2, equals that slope of 3 times x minus 5. So this is our tangent line. Right? Or and we're looking about f of 7, right? And so if we're talking about what do we get when we put in 7 here, right? Well, y plus 2 equals 3 times 7 minus 5, right? That gives us y is equal to 4, right? And so we know that if f double prime of x is less than 0, f is concave down. And if f is concave down, then the tangent line, right, if we have a function that's concave down, the tangent line is always an overestimate. And the secant line is an underestimate, right, which we could see right here, right, if I try to sketch the secant line. So this work over here shows us that the true value of f of 7 must be less than or equal to 4, because 4 is an overestimate, right? And then over here, we'll say that our secant line equation, right, which we'll get our slope for our secant line by doing f of 8 minus f of 5 over 8 minus 5. Right, and f of 8 is 3 and f of 5 is 4. So we end up with a slope of negative 1/3. And then we can use either point we want. We'll just use the point at 5, I guess. It doesn't really matter. We'll do y plus 2 equals negative 1/3 times x minus 5. And now when I plug in 4, or not 4, what were we plugging in? 7 to that, we get y plus 2 is equal to negative 1/3 of 7 minus 5, or negative 2/3. And so y, if we have positive 2/3 there, right, 7 minus 5. No, that's a negative 2/3. Yeah, that's a negative 2/3, but we'll go back and fix this all, because clearly what we've done here is I said f of 8 minus f of 5, and f of 5 is negative 2, not what I wrote there, which was 4. Right, so minus negative 2, so that gives us 5/3 here. So now when we write our tangent line equation, we're going to have y plus 2 equals 5/3 times x minus 5. And when I plug in my value of 7, we get y plus 2 equals 5/3 of 7 minus 5. 7 minus 5 is 2, and 2 times 5/3 is 10/3. And if I subtract 2, right, we're going to get y is equal to 4/3. So our secant line approximation will be 4/3, which means that f of 7 must be greater than or equal to 4/3, since that secant line approximation had to be an underestimate. And they gave you 4 points there for this problem. They gave you 1 for the tangent line equation, 1 for showing that f of 7 must be less than or equal to 4, 1 for the secant line equation, which was right here, and 1 for showing that f of 7 must be greater than or equal to 4/3. And you had to have this little explanation that since it's concave down, the tangent line's an overestimate and the secant line is an underestimate. And that's it. That's the end of this function FRQ, which is question number 5 from the 2009 AP Calculus AB exam. All right. This is question number 5 from the 2009 Form B AP Calculus AB exam. It's a function FRQ, where we're given, first of all, a graph of f prime, and we're told that f is a twice differentiable function on this interval from negative 1.2 to 3.2. We know that f of 1 is equal to 2, and f prime, we've got its derivative here. And we also know that it crosses the x-axis at negative 1 and 3 with a horizontal tangent at 2. And so we've also got this other function, g of x, which is defined as e to the f of x. So we want to write the equation of the tangent line to g at x equals 1, which means we need to figure out what g of 1 is and what g prime of 1 is. But g of 1 is e to the f of 1, and we were told that f of 1 was equal to 2, so this is just e squared. And then we need g prime. So g prime is the derivative of e to the f of x, which is e to the f of x times the derivative of f of x. So f prime times e to the f. So we want g prime of 1, which will be f prime of 1, times e to the f of 1, which we already know is e squared. And we just found that already. So then we need to figure out what f prime of 1 is. Well, looking at the graph of f prime, right? F prime, that's negative 1. F prime of 1, they gave us the point, is negative 4. So this is negative 4 e squared. So we just write our equation, y minus that y value, which is going to be y minus e squared, is equal to our slope of negative 4e squared times x minus 1. And that was worth 3 points. 1 point for just having an expression for g prime, 1 point for having the values of g and g prime, and 1 point for the equation. In part B, we're looking for all values of x at which g has a local maximum. Well, we already said that g prime was equal to f prime e to the f of x. And we know that e to any power is never going to equal 0. Right? And that's what we're doing here is we're looking for a local max. So when is the derivative equal to 0? So really, it's just when is f prime of x equal to 0? Are our only possibilities. And we know f prime of x equals 0 when x is -1 and when x is 3. Right? And because e to the f of x is always going to be greater than 0, no matter what we plug into it, all we really care about is the sign of f prime to figure out when we have a max. So we can say that g prime goes from positive to negative, because that's when we have a maximum, right? Is when a function's derivative goes from positive to negative. Right? And so, well, the only thing that's going to tell us that is when f prime goes from positive to negative. And f prime goes from positive to negative right there at -1. So g prime is going to go from positive to negative at x equals -1. So only max of g is at x equals -1. And that's it for part B. They gave you 1 point for the answer with the justification, which needs to include that g prime is going from positive to negative there, and probably that we can see that e to the f of x is always greater than 0. In part C, they give us the second derivative of g and ask us, is g double prime of -1 positive, negative, or 0? Well, g double prime -1 includes an e to the f of x, right? So e to the f of x is, as we already said, always positive. And then f prime of -1, so we'll find f prime of -1, so f prime of -1 we know is 0, so this part is just going to equal 0. And then f double prime of -1 is just going to be the slope of f prime at -1. And we can see that the slope of f prime at -1 is negative, so that's less than 0. So what we've got is a positive, right? E to the f of x is positive, times a negative here, which means that g double prime of -1 must be less than 0, or it is negative, right? And we'll probably make a note that f double prime is less than 0 because f prime is decreasing there. Right? We know e to the f of x is always positive. That's just a known fact. Right? E to any power is always positive, and f prime is 0 because we can look at the graph and see that. And so they gave you 2 points for that, 1 for the answer with some justification, some work to back it up. And here in part D, it asks us to find the average rate of change of g prime, which is the derivative of g over the interval from 1 to 3. So to find the average rate of change of something, we just need to do the slope between the 2 points. So g prime of 3 minus g prime of 1 over 3 minus 1. And so I believe we already did g prime of 1, I think, earlier. I believe g prime of 1 was negative. Yeah, g prime of 1 was -4e squared there from part A. So we're going to have a minus 4e squared. So that's going to end up with a plus in between because g prime of 1 was already -4e squared, right, for g prime of 1. So now we need g prime of 3. Well, g prime of 3, we know that g prime was f prime and then e to the f, right? So we need f prime of 3, e to the f of 3. So f prime evaluated at 3 is just 0. So really, we're just going to end up with 0 plus 4e squared. Doesn't matter what e to the f of 3 is. We just get 4e squared over 2, which is just 2e squared. And they gave you 2 points there, one for just setting up the difference quotient and one for the final answer. And that's the end of this function FRQ, which was question number 5 from the 2009 Form B AP Calculus AB exam.